All right. Welcome everybody to this webinar series on Beyond Diagonal RIS, organized by the special interest group within the IEEE Communication Society. Today is my great pleasure to introduce you our speaker, Qingqing Wu from Shanghai Jiao Tong University. Qingqing is a very well-known figure in our field, as he's the father of IRS or RIS. So let me very briefly introduce him before giving him the floor. Qingqing is now associate professor with the Shanghai Jiao Tong University, and his current research interests include IRS, unmanned aerial vehicle, UAVs, communication, and MIMO transceiver design. He co-authored more than 100 IEEE journal papers, with many ESI highly cited papers, which have received more than 40,000 citations, and is listed as the Clarivate ESI highly cited researcher since 2021 and Xiaomi Young Scholar. He serves as editor for many IEEE transaction journals and letters, and he is the lead guest editor for IEEE Journal on Selected Areas in Communication, and workshop co-chair for many IEEE conferences, and serves as the workshop and symposia officer of RIS Emerging Technology Initiative and research blog officer of the Aerial Communications Emerging Technology Initiative. So let me remind you very briefly the rule of the webinar. The talk is expected to last approximately 50 minutes, during which the audience will be muted. But if you have any question, please feel free to type them in the chat. And at the end, we will have a Q&A session of roughly 10 minutes, where you will be able to raise your hand and ask directly your question, or otherwise we will pick some questions from the chat. So enjoy the talk, and Qingqing, the floor is yours.
Okay, thanks for the introduction, Mato. And let me first share my screen first. That's okay. Sharing the screen. Okay, can you see my screen now?
It's loading.
Okay?
Yes, I can see.
Okay, that's great. Okay. And firstly, I'd like to give my thanks to Professor Bruno and also Mato. And I'm very honored to give this talk. And actually, I think in the last few months, one day Professor Bruno visited me, and he also gave a talk in my university, talking about talking about the Beyond Diagonal Intelligent Surface. I found that very interesting. But this talk was invited almost like, I think half a year ago. But because of, some other, service issues, so I choose to give the talk today. And as many of you have known this, that I've been working on intelligent reflecting surface for a couple of years. And it has received a lot of attention from not only from the academia, but also from the industry. As we know that, currently, like, the leading IT companies like Apple, Qualcomm, Samsung, and they all have the, intelligent surfaces related patents. If you search on the website, you can search, like Apple, they also filed some patents on the intelligent reflecting surface, and also Qualcomm, almost all the, and also British Telecom, I guess to my best knowledge, almost all the leading IT companies, they have this kind of patents. Although in the academia, we don't care about too much about the patents, but it shows that, it's a practical, use cases, in the potential, and its potential in the future. So the talk of this, the title of this talk is called Movable Intelligent Reflecting Surface for Communication and Sensing. So from the title, basically, you see that we are going to talk about some movable perspective. Okay. But before that, I'd like to go through some of our previous work on the, like a traditional intelligent reflecting surface for communication and sensing. But maybe because of my past research not actually highly related to the beyond diagonal, reconfigurable intelligent surface. But I think most of the architectures and most of the scenarios and algorithms, they could be extended to the case with the beyond diagonal RIS. Okay, that is proposed by Professor Bruno, right? And he has been very active in promoting this direction. I guess in the last few months, he has, traveled to a lot of, especially in China universities, and, almost, give, I think, at least 20 talks. Okay. But anyway, as I mentioned, most of the principles are applicable for the case with the beyond diagonal RIS. And maybe using the beyond diagonal RIS, the performance could be improved further, but with improved hardware complexity and cost. But that's could be something in the future for research. So in terms of back to the IAS 80, the sensing, as we can see here, actually the sensing is, as we know, that is also one of the most promising, scenario in the future 6G, like in the robotic network. Everybody, right now talking about AI and robotics, right? Because they are very, useful. And Elon Musk, they also have the robotics, can do a lot of things today. So, but in this kind of a factory scenarios, and if you want to sense, if you want to coordinate all the robotics, robots, and we also need like a sensing, this kind of not only communication but also sensing, because we want to sense the target, the position of the target, and also the angle, and also even their gestures or something. And the resolution could also be requirement could also be very high. And also for the future, that is our vehicle network, right? As we can see here, because but for our traditional, the service can be deployed, right? From the deployment perspective, it can be deployed like in the first scenario, deployed in the free space, like on the walls, on the ceilings, right? But it could be also deployed, directly on the surface of the vehicles, surface of the targets. And right, it could be like what we call it as the target mounted IaaS, right? So, but in this kind of case, as we know that actually the vehicles can also reflect the signals, randomly, but its reflection is random, right? Because it's surface is not that flat and it cannot be controlled. But if we use some parts of its surface to be deployed with the IRs or RIS, and probably we can control the reflections. We can have the more stable echo signals, and which could be used to improve the sensing resolution, and also improve the sensing reliability and something. Okay, this is what we call it as a target mounted. Okay, this is what we call it as deployed, in the environment. So in this case, it could be considered as like an anchor point, right? It could be or you can consider as a reference point, because beyond the transmitters, we could have a lot of this kind of anchors or reference points, and by using this kind of reference points, we can localize and we can sense other objects. Okay, but this could be the two most useful deployment use cases in our practical wireless networks. But beyond this, there could also be some like studies regarding the advanced IaaS architectures, like what we call a traditional fully passive IaaS, without a sensor. But it could be also something like it's a hybrid IaaS, which means that it not only concludes the passive elements, but also include the active sensors, like active elements for amplification, or the sensors for sensing, like for the signal processing for the angle sensing or something localization. Okay, so this is kind of what we call as a hybrid IaaS. Okay, it could be amplify the signals and reflect them back to the base station, or the sensors on the surface on the IaaS can also, directly process the echo signals from the target, such that the subtract the, location information. And also, because the hybrid IaaS and also the base station, both of them can get the information, location information of the targets, so they can also do some kinds of like, integration. The integration could be, finished complete at the signal level, and also can be completed at the, results level. That is the location level. For example, the hybrid IaaS can use some, computing devices to directly compute the angle or location information of the targets, and then send this kind of information to the base station. Then the base station can do some like average or something. But the hybrid IaaS can also directly process the, sense the signals to the base station, such that they can, process that at the signal level. So basically, but as you may also know that this hybrid IaaS can also be replaced by like a beyond IaaS, beyond diagonal IaaS, right? Which is also, a promising study. And basically, all the research here can be revisited by using a new IaaS architecture. This is what I mentioned. From the deployment perspective, we have some scenarios, but considering different IaaS architectures, we also have some studies. But regarding for the IaaS for the anchor for sensing, and the challenge here is how to balance the localization, accuracy, and also the scanning overhead, because the IaaS need to scan, this kind of targets. And one solution could be applied the hierarchical codebook-based IaaS reflection design. Okay, this is one promising approach. And because in practice, the IaaS, the number of the elements is very large, and we have to use some hierarchical codebook and to reduce the, reflection overhead. But for the target mounted IaaS for sensing, and because the target mounted IaaS need to reflect the signals directly to the, transmitter, either the receivers or the base stations, and such that the base station can extract the echo signal and to obtain the location or angle information. So the challenge is that how to design the IaaS phase shift to reliably direct the echo signal towards the intended receiver. This means that it could be, it's in this case, the vehicle's surface is not just a randomly reflection devices, but also a highly controllable devices to reflect the signals to the base station, such that to improve the reliability for sensing. And also for hybrid IaaS, they could be like how to determine the optimal data processing strategy. As I mentioned, there could be some integration, because either the IaaS can do the sensing, the base station can also do the sensing, and how to do this kind of signal processing, and also how to strike the balance from the perspective of the deployment of the passive elements, active elements, and also sensors. Considering, because in practice, usually we have a limited hardware cost or hardware budget, and how to, allocate this kind of budget to these kind of devices. Actually, we have one magazine paper that is intelligent surface empowered integrated sensing and communication, which could be, if you have an interest, you can read. But regarding the IaaS for ISAC, actually they could be because ISAC includes the communication and also sensing, but actually they are essentially different traffic requirement. And by saying this, when we talk about how to use RIS to satisfy their requirement, then the RIS can make different functions. For example, for sensing, the communication, the function of the RIS is mainly to increase the channel gain. Okay, increase channel, and not only increase the channel gain, but also increase the channel correlation. Because when we sense the target, we hope that the beams could be as focused as possible, right? Because for the sensing targets, they don't care about what is the message, what the message is, right? Because they are not going to decode the signals. They just reflect the echo, receive the signals back to the receiver. Okay, so they don't care about what the message is. This is very different from the information, because information communication. Because communication receiver needs to decode the signal, so they care about not only how strong the signal is, but also what the signal is. Okay, is it you desire the signal, or is it interference? But for sensing, it doesn't matter. Even the interference, sometimes can also be used for sensing. Okay, this later we have a scenario that could be used for this. So, and this essentially is so from this perspective, sensing is kind of like the communication like a multicast. If you have the multicast is try to is to try to coverage, send the same information to all the users. So then all the users, they also don't care about what the information is, because all the information are useful. Okay. And this is very different from the unicast. Okay. And for unicast, I mean that this is what we have done in the past several years. And the function of the RIS is to improve the channel gain. And also because they are, for unicast scenario, they are multi-user scenarios, which means that the signals for one user is usually the signal, the interference for other users. Then we need to, decrease the channel correlation, right? Otherwise, the interference will be very strong. So, and in this kind of case, the function of the RIS is to decrease the channel correlation, okay? And also with the high rank, because this is what we call actually, especially in using massive MIMO, and also by using the distributed IRs, we are going to improve the rank of the channels. Okay. So as long as you know that the RIS and IRs can have different functions for the sensing and communication, then you know the fundamental thing is that how to balance the channel for communication and sensing. Okay, because the sensing channel and communication channel, they have different requirement, and this kind of a balance can be either achieved by using the reflection. This is from what we call as the channel balance. That is by tune the IR's phase shifts. And another perspective is the deployment balance. Okay, like we can use the fixed deployment, or like a sufficiently large IRs, or deployment of multiple IRs, smaller IRs, or we could also consider the target amount of IRs or distributed IRs, as we can say. Okay. And there are also some reciprocity, because between the communication and sensing, as even without IRs, we know that communication sensing can be used to improve the performance of the communication, right? Because we can first sense the essentially you can consider channel estimation is a kind of a sensing, right? Because we can first sensing the angle, in the line of sight scenario, we can sense the angle of the target or angle of the users, and then we communicate. And if you are sensing, if you have a good sensing result, and you can get a more accurate of the target, more accurate location of the target, and then you can improve the communication performance. On the other hand, but communication can also be used for sensing. Okay, like we can use the communication, like usually we have the channel estimation, and the channel estimation part can also be used as the sensing, and so they have this kind of a mutual assistance between the communication and sensing. So one study is how to theoretically characterize the boundaries of the sensing and communication performance under the scenario of the IRs. Okay, and also is sensing or communication always leads to the performance improvements for each other. Okay, we're going to answer these questions in this talk. And actually, we have a few works, and that is IRs for sensing. And so the first work, I'm going to quickly go through these parts. And the first work is the IRs enabled multi-target sensing. Okay. And traditionally, if we use the base station for sensing like this, if we have the line of sight for sensing, the strategy is very simple, right? The base station just need to send multiple beams, or send each of the beam, scan the beam, okay? Like if you want to sense the target in the 30 degree direction, they just send the beam towards the 30 degree. And then if we get the signals back, sufficiently large and, beyond a threshold, then we can say that, this is called as a detection. We can say that in this direction, we have the target, right? But if we do not receive if the base station does not detect sufficiently large signals, echo signals, then the result is that, it has no signal in this, it has no target in this direction. This is actually a very straightforward idea. But in the case of the IRC, it's going to be complicated. Okay. The reason is that if we use the base station to direct, sense the targets, the angle is different. As you can see, this is a 30 degree, 20 degree, or 10 degree, and it has difference. But if we use the IRs, as you can see that from the IRs to the targets, it has different angles, like 30 degree or 20 degree. Yeah, it is essentially the same as that of the base station. But when the signals, are reflected from the targets to the IRs and then eventually to the base station, as we know that this link from the base station and the IRs link, all the targets, the echo signals, they share the same link from the base station to the IRs. Okay? If we do not do something, then they are going to be highly correlated. Okay? Highly correlated means that you cannot, even this target, locates in the 30 degree direction of the IRs. This locates in the 20 degree direction, but from the base station, all the echo signals are coming from this direction. Okay? It has no difference. Okay? Then how to resolve this problem? And then we propose we developed an innovative scheme that is to make use of what we call as a zero forcing idea. Because what we call it as a zero forcing is what is at the base station side. If you want to send signal S1 and then to this target and send S2 to this target, right? And then the signals, if S2 has the very low signal at the target 1, okay, at this place, and then the echo signal from this target in terms of the S2 is very limited, right? And then by using this kind of schemes, then we can at the base station side we can detect the signal of S1 and S2. For example, if this target is S1, this target is S2, which means that the S2 signals to the direction of this target is very limited. So at the base station side, if we detect the echo signals of S2, it could only be from this target, okay? And on the other hand, if you detect a sufficiently strong echo signal in terms of the S1, we can conclude that there is a target here, okay, in this direction. So the fundamental solution is that we're going to establish the one-to-one mapping to overcome the correlation between this base station and IRS channels, okay? And by doing this, we're going to formulate, we're going to develop a hybrid time division, what we call a sequence, because each of the target is associated with the sequence. It's kind of like a traditional, like a sequence, CDMA, this kind of, okay? And then we can do the joint beamforming and grouping, and by solving this kind of problem, eventually we can trade off the beam pattern gain and also the sensing frequency, okay? And this is all some of our simulation results. As you can see that we could have, by using the IRs, we can establish, the beam patterns, different beam patterns toward the targets. And also, as the, number of the targets increases, and our proposed scheme can also achieve a high, SIR, okay, in terms of, and also it leads to the high sensing accuracy. And also we could achieve the high And also we found that there is a trade-off between the sensing frequency and beam pattern gain, which means that if we want to sense the target, at a very high frequency, then the beam pattern gain could be reduced. It will be reduced. But if we want to sense the target at a low frequency, and then we can have a higher resolution. Okay, this is kind of a trade-off. But that is only to to develop a scheme to achieve the sensing. But in practically, we also have we're going to use the multi-IRs to achieve the sensing. But for the first work, as you know, that all the signals are processed, the echo signal are processed at the base station. But as I mentioned, if we could have some sensors at the IRs side, we can also directly process the signals. That means the IRs is also a sensing device. Okay, although it cannot transmit the signals directly. It's not like a base station to transmit the signals, but it can receive the signals, but and sense the direction of the targets. And by using this kind of architecture, the biggest advantage is that in the first scenario, we have 4 links, right? This link and then the forward link and then back to this link and back to the end. We have 4 links, but so the path loss will be very high. But in this case, by deploying some sensors around the IRs, we could reduce the number of the links from 4 to 3, and this could improve the sensing performance. Okay, that means essentially is to reduce the path loss. Okay, another advantage is that we can use this kind of distributed IRs. Why do we use the distributed IRs? As you can see that this is like in this case IRs is, as I mentioned, is the anchor point. It's kind of like a monitor or camera. Actually, sensing is kind of like a camera, right? Because by using this camera, the IRS-1 is a camera and to see the targets in this direction. And also we can use the camera 2, IRS-2 to see these targets. Because we have this kind of distributed information, and also they look at the targets from different angles, from different perspectives, we could have more information. We could have more concrete and vertical and horizontal and whatever information of the targets. And this could be useful to help improve the localization, accuracy of the targets. Okay, this is another advantage. But the challenge is that how to achieve the sensing signal, how to achieve that the sensing signal is reflected by each eye are orthogonal to each other. Otherwise, there is no diversity gains. Okay, and challenge 2 is that how to coordinate the estimation of the target's position. Okay, so and in this kind of cases, we propose some localization strategies, like we use in this work we use the time of arrival estimation, because we estimate, as we know, that this would be the first link, second link, and to the targets, and then reflected back. But as we know that the information from the IS2 can also be reflected by this target and also to the IS1. Okay, we also have this link. So essentially, you have this kind of from IS1 to target IS1. This is a circle. Okay, directly a circle. But also we have IS1 from IS1 to target, but it could be reflected to IS2. Okay, and the sum distances will not be changed. So it's kind of like an ellipse, and also from the IS2 to IS3 and so on and so forth. And we have this kind of protocol. Okay, we have this kind of characteristics. And then our objective is to min-max the CRB of the localization of the targets. And also we consider the orthogonal, and this is the power constraints, and this is also some other constraints for the optimization. And in this work, we just propose a 2-stage algorithm. And the first stage is to activate all the reflection elements and optimize. And the second stage is to inactive the reflecting elements without a power allocation in stage 1, and then optimize. And eventually we are minimize the maximum of the CRB of the targets and by jointly optimize the active beamforming and passive. And we could use some like, iterative and alternating optimization methods. And also we also consider the compare with our the one stage estimation methods, and also other benchmark schemes and equal power allocation, and also random phase shift. We can achieve the localization accuracy gain. And particularly we can see that the N-reflecting elements and M sensors provide actually this is proportional to the n square and in the denominator, and also m 1 over m gain in the localization accuracy. But just now we only use the time, that is time of arrival. That is essentially a distance based. That is, we calculate the distance, then we estimate the time of arrival, and then we have this kind of a circle and ellipse. But we also have some other estimation strategies. That is directly estimate the signal, the angles, right? That is what we have done in this work. In this work, not only we estimate the time of arrival, but also we also estimate that we introduce the additional angle information. Okay, this could be used to further improve the localization. And also we focus in this work, we focus on the estimation algorithms. Okay, and particularly we use the cascaded delay estimation that is achieved by using a matched filtering. Basically the scenario is almost as the same. Is as the same as the previous one, the considered scenario, but we just add the angle information, just one step further. But for the angle estimation, we use the atomic norm minimization, which we first constructing a 2D atomic norm set, and then we do the joint optimization estimation based on the observation samples. And then eventually to solve this problem, we use the low complexity solution based on the ADMM. And because we also need to estimate the angles, we have a 3-stage algorithm. That is first, we first estimate the segmented delays. That is tau k and tau l from the cascaded delay, and then we could have a coarse location as the location of the targets, and by ignoring some like second order terms, in the received signals. And in the stage 3, and we have refined the estimation results, and by using the SO's second order information to improve the information estimation accuracy. Okay, so and also we consider like the previous scenario, like a semi-passive, that is to deploy some sensors around the IOS, and also fully passive. The fully passive one which means that all the work needs to be done at the base station side. This is like the first work, and this is like the second work. So eventually we also demonstrate by using this kind of, by introducing the angle information, angle estimation, we can significantly improve the MSE performance as compared with other benchmark schemes. As you can see that our proposed method is able to achieve significantly low MSE as compared with other like music or aspirate or couple methods. Okay, but as I mentioned, all the previous works are based on the environment IaaS, which means that IaaS is deployment around the environment. Okay, a distributed deployment. But in practice, it could be deployed, as I mentioned, a target mounted IaaS. Okay, so the purpose is that as we know that if you deploy in the environment, we still have 3 hops, right? Because as you can see, the first hop, second hop, and then back to the IaaS. Even though the IaaS have the sensors, we still need to have 3 hops. That also leads to the the high path loss in practice. But we also have another strategy, that is reducing 3 hops to 2 hops. And how to do that? That is by deploying the surface on the surface of the targets. And in this case, as you see, this is the first hop, this is the second hop. Okay, right? As you see that our 3 works and reduce from the fully passive one to the hybrid one. We reduce the path loss from 4 to 3 and to 2. Okay, to improve the localization performance. But in this case, it could be different with what we have done in the previous works, because if we consider a cellular scenario, and each of the vehicles, they could have some surface that can be controlled like IRs. And then the purpose of using this kind of surface is to reflect the sensing signals from the base stations and reflect them back to the base station. So then there is a fundamental trade-off between the association optimization between the base stations and also IRs. As we know that on one hand, with a given duration, if each IRs tends to establish the association with more base station, because if the IRs can be associated, can be echo the signals, reflect the echo signal to the more base stations, it could have more like what we call as the diversity, macro diversity gain. Because like base station 1, 2, 3 can also reflect the echo signals from these targets, and then they could be jointly to do some processing, and then have the more can improve the accuracy of the localization. But on the other hand, more associations inevitably reduce the dwell time of the HIRs, resulting in decreased measurement accuracy, and also leads to greater interference between different base stations, because they are also multi-user interferences. Okay. So, and then we also develop a scheme that is to min-max the CRLB and of all these targets. And also we have some constraints to restrain that each of the base station is can only be used for each vehicle. And then by using this, we formulate this problem. And the first question is that how many base stations do the IRs needs tend to associate with? Okay, this is not only from the optimization perspective, we want to answer these questions, and we are we prove that IRs tend to associate with very few base stations to focus. Because the objective, the main reason is that to focus the reflecting power for sensing performance improvement. Okay, otherwise if this is sometimes like our traditional water filling strategy, because we want to focus the reflection power to for a very few base stations. Actually, our numerical results also demonstrate this result. Like if we shift we can associate a base station number 1 and 2, and we can achieve the performance of 90%. We have 3, we have the 80%. We only have the 80% loss. Okay. So actually, in our practice, it is usually sufficiently for IRs, to be associated with 2 to 4 base stations for localization accuracy enhancement. Okay. And this work is published in TCOM, and also we have we can also see the trend as you use a large number of base stations. Definitely you will further reduce the CRB, but eventually it will be saturated. So in practice we don't use because at the very beginning of associated with very few base stations, the CRB is significantly reduced. Okay, this is a practical insight. And also in practice, we also have the IRs for ISEC. And also because this is, as I mentioned, sensing can be also used for communication. Okay, the reason is that at the very beginning, you may not have the sufficient information of the targets. So if you directly communicate with the targets, the communication efficiency could be very low. The transmission rate will be very low. Okay, because maybe you cannot, send the beam directly to the direction of the target. So this is what we need the sensing, part, the sensing stage. Okay, basically we develop a scheme that is consisted of these 2 stages. The first stage is that jointly sensing and communication. But in this, as we know that the surface is what we call as the IO that is intelligent omnidirectional surface. what we call omnidirectional, that the iOS not only reflect the signals back to the IaaS, to the base station, but also the penetrated signals can also be used for communication with the users inside the vehicles. Because as we know that some users inside the vehicles, they also want to watch videos, or maybe some customers do the online gaming or something like this. So then the iOS can do this simultaneously. Okay, sometimes it is also called as a BD-RIS. Okay, simultaneous reflecting and reflection, transmitting and reflection. Okay, so basically the echo signals, that is the signals reflected from the surface is used for sensing, but the signals transmitted from this surface is used for communication. So in the first stage, that is the joint communication and sensing. Then the second stage, after the joint sensing and communication, where because our ultimate objective is to communication in this scenario. Okay, then we have this kind of a time trade-off. That is the trade-off in the time domain. Okay, the insights is very simple. If you spend a lot of time in sensing, in joint sensing and communication, stage, and then the time left for the communication will be reduced. Then it will reduce the communication rate, the total throughput. But if you use on the other hand, but if you use a lot of time for sensing and communication stage, it can improve the location information of the targets, and then it can also improve the beam, which means that we can focus the beam directly towards the targets, and then you can improve the SNR of the users inside the vehicles. It can also be used to improve the communication performance. So there is a trade-off between the time allocation. This is the first point. The second point is that even inside the sensing and communication stage, as we know that we have a total number of n elements. If we use more elements or reflect more power back to the base station side, then less power will be used for communication for the users inside the vehicles. On that, and vice versa. If you let the signals, a lot of signals, signal power is used for communication, then the echo signals will be, the strength will be smaller, the power will be smaller. Then we'll reduce the sensing accuracy. Okay, so that inside the first stage, there is also another fundamental trade-off, that is in the power domain. That is, if you want to use more power for communication, improve the communication rate, but then the sensing accuracy will be low, and it also decrease the total throughput, particularly in the latter stage. But if we spend a lot of signals for sensing, although the sensing accuracy can be improved, but in the first stage, the communication throughput will be reduced. So there are two trade-offs between this considered scenario, and we also developed a two-stage ISAC protocol. The first stage, as I mentioned, a joint sensing and communication stage, we use the extended Kalman filtering, and for the communication only stage, then we estimate and track the targets. These results will be used. And our objective is to maximize the total rate among the users. Okay, by jointly optimizing the beamforming, phase shift, and the duration of the time allocation as well as the power allocation. Okay, this is the actually problem formulation, and particularly the most of the important question is that whether is the joint sensing and communication stage needed. Okay, because if we at the very beginning, because we use the Kalman filtering, if at the very beginning, if we have already very good initialization of the target information, location information, maybe the joint sensing and communication stage may not be needed, because it also reduces the time for communication in the latter stage. So then we derive at the optimal solution. We found that if this condition is satisfied, it means that the joint communication and sensing stage will always be needed. Okay, which means that the sensing is always needed for communication. Okay, but otherwise it's not needed. Okay, so we derive this threshold. Okay, and also we prove that we also demonstrate this as you see that this is our sensing condition, although it's very low. Okay, and at the very beginning we don't need to allocate time for sensing, but as long as our parameters increases, and you will see that we will have the sensing requirements. And also we found that by using this strategy, the estimation accuracy can be improved, and also to help improve our communicate eventually improve our communication rate. And vice versa, we can also say that by achieving the same achievable rate, we can save significant power. Okay, and also as I mentioned, the second trade-off is the power allocation. That is the reflecting power ratio. That is the power reflected back to the base station for sensing, and also the power transmitted to the users inside the vehicle for communication. And in this joint and sensing stage, okay, this is the optimal trade-off power reflecting ratio. Okay, so fundamentally, by deploying the IaaS, we could have this kind of trade-offs, and also the sensing most likely can be used for improve the sensing performance. And also we have another work that is what we call like a mutual assistant design. Directly based on the previous work, because the previous work, as we know that traditionally from the communication perspective, we know that multi-user interference is the very bad signal, right? Because the signal used for each user is interference of other user. This is why we want to reduce the interference. But as I mentioned, from sensing perspective, we don't care about how because we don't decode the signals, so decode the information. So the message of the signals is not important, but also the strength of the signal is important. And in this kind of cases, the traditionally that means interference can be used for sensing. For example, the signals sent to this user for communication, because there will be some leakage, the signal leakage to other users. Traditionally, this is like what we call as interference. But if we can use the base station, can also treat it as this kind of echo interference as the sensing signals for this vehicle. And because the base station can get the information, can get the location information from the echo interference or echo signals, and then they can help estimate the next vehicle. And after we got the location of the next vehicle, and then we can communication better with the next vehicle. Okay, this is kind of we propose also a new protocol that is iterative one. That is the first stage is like the sensing the first user, and then in the second stage, that is a simultaneous communication and sensing. That is when we are communication with the first user, that is C1 communication. We are also using the signal, this part of signals that is traditionally considered as interference is going to be used for sensing for the vehicle 2. Okay, and vice versa. And first, the signals communicated with the user K is going to use for the is going to be used as a sensing signal for the K+1. Okay, and by using this kind of a protocol, which means that sensing is used for communication, right? Because using the sensing, in the former stage, we can have the communication in the next stage. But at the same stage, the communication signal is also used for sensing. So this kind of joint design, okay? That is CK is for communication for refraction mode, or you can also call transmitting mode. The sensing is the reflecting mode. So this, the red arrow is sensing assisted communication, but the blue one is the communication assisted sensing. And by using this kind of a mutual assisted protocol, as we see that this is our proposed design, by the achievable rate, that is communication rate and also sensing requirement, we can achieve the better, trade-off as compared with other schemes without this kind of mutual assisted design. That means our proposed design can significantly improve the trade-off between the sense and communication. Okay, if you have the interest, you can also read our paper. And also we have some other works like, actually the previous work can also be considered as a movable, but it's move at a very large scale because on the vehicles. But it could be also be achieved at a very small scale. Okay, like move intelligent services for communication. Okay, so the idea here is very simple because we also discussed a lot of this industry guy. The industry, they care about the practical use cases. They found that they say that if you can, traditionally we know that if you want to use the IRs for beamforming, how to use that if we tune the phase shifts, right? To tune the phase shifts such that we can achieve we achieve one beam. That is okay, like this we can achieve one beam. But as I mentioned, you need to tune the phase shifts of all the elements. And in practice, if the number of the elements is very large, in the signaling overhead and also the power consumption is also not negligible. Can also not be ignored. And this motivates us to consider a completely passive IaaS, which means that this IaaS, as I said here, is the totally passive one. Once it is fixed, once it is manufactured, it cannot be tuned anymore. That is sometimes we call it as a static phase surface, but it is pre-designed. Okay, which means that the phase can be can be designed in advance. But once it is fixed, it is fixed. It cannot be tuned anymore. The biggest advantage of this kind of design is that as long as it is used for communication, we don't have any energy consumption for this surface, for this IaaS, because the surface does not need to tune the phase shifts anymore. Then it brings another problem. That is, if the phase shift is fixed, as in our traditional scenario, how to do the beamforming if the user moves? Okay, right? Because if the user moves traditionally, if the user moves from this from here to here, then we need to tune the phase shifts direction to this direction. Okay, but if we cannot tune the phase shifts, how can we achieve this kind of the beam sweeping? Okay, and this is what we have done in this work. That is, we call it instead of using the to tune the phase shift, we can use two static IaaS, two static surface, and the two static surface is to enabling dynamic beamforming with static phase shift by mutually position shifting. Okay, as you will see, it's the main idea. That is the fundamental thing is that to bridging the purely static and fully dynamic approaches with the mechanical reconfigurability. Okay, as you can see, the main idea will be here. As you can see, it's kind of like it has a very good. This is a very good example. Is here. If we have two surfaces, each of the surfaces is phase shift are fixed. Okay, but if we are moving the first, these two surfaces can be also a smaller, with a larger one. It could also be two circle. Okay, it could be a two circle, like one surface looks like this, and also one surface looks like this. Then they can rotate in different directions. Okay, by rotating this, just like okay, let me give the example. By moving this surface around this the large surface, as you see that because the total here we consider the reflecting. That is you can consider as a reflecting. That is transmitting. Transmitting, that is that the signal will be first coming from these two, needs to penetrate these two surfaces. Okay, which means that the total phase shifting is the phase of the first layer and also plus the second layer. So that is kind of like one plus. That is kind of like the first layer plus the second layer. Okay, so the first layer is if we give the phase 1, then plus in the second layer we give a phase 2, then we will have a phase 3, right? This is and by moving this kind of the first layer surface, as we know that although this one is not changed, but the second one could also be changed. For example, if we moving this surface from this position to this position, as you see, if we move the whole surface from this to this one, then the first elements, the theta 1 is not changed, but the theta 2, the corresponding theta 2 is from this in the bottom one, and the bottom is changed, which means that here we could have the phase 1 plus phase 2 spot, phase 2 head or phase bar, and then we could have another, with phase 4, we could have new phase. Okay, and by moving this kind of surface, the whole surface, actually can achieve a lot of patterns. Okay, this is, as you can see, by using this by synthesize this kind of patterns, we can achieve the beam scanning. Okay, as you can see here, we can achieve the beam angle in this direction, and also when we move here, we can achieve in this direction, and also we can have this direction. Okay, and this is how to modeling our how to previously design this. This is actually a very very innovative idea in this work. That is, we design 2 static IR surface, but as you know that if we move this kind of surface around this large surface, we can beam screen, we can scan in different directions. Either it can be used for communication or for the sensing or localization. Actually, we consider it as a coverage problem, and we formulate this problem, and then the optimization variable is how to jointly design association and also the prior designed phase shifts. Okay, so and eventually you can also have we also have some results. If you have the interest, you can have. And beyond the simulation results, actually we also made this demo, and I can see that we do this as 12 gigahertz, and this is 40 elements of multi-40 elements, and so it's kind of like we have these 2 layers, and as you can see here, if we move the first layer and with the different shifting, position shifting, we can achieve the different beam scanning directions at the different angles. Okay, this is our experiments results. Okay, and also we use a slider track, and this could be mechanically started rail, and this is a power supply and the controller. This is 2 hours of the surface, and by having some positionable misplacement, we could have some we can transmission this QPSK, this kind of, and we also transmitted some video signals or the picture signals, and this is our demo in the indoor scenarios. Use the USRP and also 2-layer surface. And but we also have some other designs. This is only for beam scanning, but for communication for communication, we also have other considerations. Like if we have multi-users, and how we maximize the total, all the minimum user data, minimum user rate. Okay, and we could have this kind of optimization problem, either to minimize the total throughput or the total minimum user throughput, or the total user throughput maximization problem. And this because when we are moving the first of the IaaS, and then when we can allocate a different time to different users, okay, and then we can use some, but this is a very complicated problem, and we use some GSC inequality, and also a penalty based method, and also jointly with the BCD and NCA to and also manifold optimization to solve this problem. So if you have the interest, you can, we can significantly, by using the biggest, as I mentioned, the biggest advantage is that we can use a very low cost hardware to achieve the dynamic beamforming. But traditionally, dynamic beamforming is only implemented by tuning the phase shift. This could lead to very like a large signaling overhead, and also particularly when the communication is happening, the IOS, the traditional IOS also need to consume power because because we use the pin diode, right? Pin diode is that if it is in the is on stage, it is still using power even in the communication stage. But for this one, we don't use the power anymore for the IOS, because once its position is fixed, then it's just like two static IOS. So the power is only to use to tune the position, but tune the position is not related with communication. Okay, so this is our advantage, and also we have another work that is with static phase shift meets the mechanical reconfigurability, and also we have other panel wise, because we have the panel wise, element wise mechanical reconfiguration, because for each of the layers you can remove, like here we only have one smaller panel, but in practical we could also have several smaller panels. These several smaller panels can move independently, and then they can lead to many different this kind of new beams. Okay, and then we can do this kind of reconfiguration. Okay, and also we have some new algorithm to solve this, and this is our comparison between the static service, totally static service. We don't move anymore, but we have the panel-wise MIS, that is movable intelligent service, and element-wise movable intelligent service, and a fully dynamic RIS mean that we tune the phase shifts, but the panel-wise elements mean that we only move the position of the IOS, the first layer IOS. Okay, and also we can use that for sensing, because we have as I mentioned, as long as this two layer IOS, that is what we call as MIS, can scan the area, then we can do the sensing. Okay, but it's just it's just the sensing or communication. They are just two different functions. Okay, like we can minimize the sensing SNR, this kind of, or the PSL for the side lobe suppression. Okay, this is our new work, and we, as you can see, that we can improve normalize the beam pattern by using this kind of proposed MIS scheme, and also can maximize the worst case sensing as even the targets at the different locations. Okay. And this is also some other simulation results. And if you have the interest, you can read our very latest work online. And I also briefly talk about another work that is what we have done. That is, as I mentioned, movable is not only just displacement, just move along a slider track, but it can also be rotatable. Okay, the idea is very simple. Because in practice, actually, so far in 99% of the existing works, most of the RIS, the RIS model, the researchers in the academia or in the industry, they use the isotropic model, which means that they consider this kind of reflective minute is isotropic, okay, or isotropic in the half space. But in practice, each of the elements could be, very directional, okay, very directional, because this is just like our antenna. Our antenna in practice is also directional, okay. In practice, there is no omnidirectional antennas, okay, in practical use cases. And if we have this kind of directivity, which means that the IOS, the angle of the IOS is very important. Like because it has a directivity towards its bore site is usually have a very very high gain, but it's the side lobe, it has a very smaller beam gain. Okay, but so then in this kind of case, how to rotate the IOS? Okay, this is what we call rotatable IOS. By intelligent rotation, we can further exploit the spatial degrees of freedom. And also, we develop a practical angle-dependent channel model based on the electromagnetic magnetic field modeling. And actually, we develop a very complicated model, and we can also calculate the reflection coefficient can be expressed by this. And we have some studies like either the area coverage enhancement, which means that we can use the rotatable IS to improve the coverage of all the total area, which means that it could be max mean the SNR, or we can also have the single target SNR maximization. Okay, this is two studies. And we also have some like near optimal solution by deriving the optimal angles of the roadable IRs, and also have some proposed algorithm based on the iterative principle, and to improve our performance. And here we compare with the fixed, that is the rotatable, with the fixed one, and we can achieve the performance improvement. And particularly, and compare with the traditional fixed one, we can achieve the significant improvement in terms of the SNR. And also we extended the IS, study from the one IS to the two cooperative roadable IS, because this is just like when we are going to see something by using two mirrors, but the two mirrors, it needs to be rotated in the right direction. Okay, right. Otherwise, you cannot see this. You cannot have a very stable, connection from the transmitter to the receiver. Okay, and also we shown that the cooperative roadable IS can also achieve the scaling order to the to the power of 4, and then the here the problem formulation. Here is our problem formulation, and is to maximize the communication rate for this user, and by jointly design the phase shift, rotation, and also this kind of parameters. Okay, and also we consider like either the line of sight channel and also the rising channel, but because in practical we usually have large line of sight, but beyond line of sight we also have some like really other scattering links. This is the rising channel, and we also derive most of the results are derived in closed form solution. And this is our performance evaluation, and as compared with the traditionally fixed IRs, that is the green one, we can improve the performance, and also compare with the single one. At the very beginning, use the single one is good, because when the number of the elements is very small, then if you again split this very smaller elements into two parts, then the cooperative gain will be cannot be compensated for the cascaded path loss, because by using the two IRs we have 3 hops, right? If we use one IRs, we only have 2 hops. So this is the trade-off between the cooperated beamforming gain and also the cascaded path loss. Okay, this is just depending on which one is dominant. Okay, so you see that when the number of the elements is very small, and then the single rollable IRs is good. That is the blue one. But as long as the number of the elements is very large, then two cooperative IRs will significantly improve the performance. Okay, this is the insights of this. Okay, as you see, even for the fixed one, you can see you can for the rotatable one, you can see this transition. Okay, from the single IRs. Okay, single IS strategy to the two cooperative IS transition earlier in terms of the number of the elements. Okay, but this is the transition of the traditional non-rotatable IS, as you can see here. Okay, so basically this what we call as roadable IS. Actually, I think there have been if you consider the beyond diagonal IS, almost all the work can be revisited or can be restudied. Okay, I believe there will be some new performance and some new degrees of freedom, as I mentioned, as I memorized correctly last time. Professor Bruno, said that it can also further improve the degrees of freedom, like the rank of the channels, and also reduce the interference and something. So there could be a lot of things can be done. Okay, so I used more time than our plan. But this is the end of the talk. This is some of our reference. If you have the interest, you can read our paper online or send me an email if you have any questions. Okay. Okay. Thank you very much for this talk.
Thank you so much. Thank you, Qingqing.
Thank you.
Any questions from the audience? Please feel free to raise your hand. If not, I can maybe start with a quick question. Very interesting, the concept of a MIS, movable intelligent surface. Also because it's non-electromagnetically reconfigurable. I was wondering for the application of beam steering. I think you also showed a prototype. What's the difference, the benefits compared to having a very directive antenna, like a horn antenna, and orientating it towards the wanted direction?
Yeah, very good question. I think you get the point, right? You mean that if you can use these two layers to do this, you can to achieve the beam sweeping, right? The slider track. What you mean? I mean, your point is that you can use the routable horn antenna, right?
Yeah. What's the benefit of having a MIS rather than?
Yeah. This is I think there are a few advantages. The first advantage is from the size perspective. In practice, the horn antenna is kind of like its size is usually large, and it's because it's as you see it will be like usually for the horn antenna it is the three-dimensional one, like, right?
Yeah.
It is three-dimensional. But in terms of the MIS, we could have two layers. The layers can be manufactured as thin as possible, so we can reduce the size, the total size. Okay, to the it's kind of a surface one as compared with the horn antenna. That is what we call it here. Basically, the two-dimensional one, but for horn antenna is the three-dimensional one. Okay, this is the first because in some practical scenario, like in the surface of the building, if you use the horn antenna, that would be the first is not beautiful. The second one is that it will cause other issues like wind and weather issues. But if you use this kind of two-dimensional, you can just make it as the like a frame, like a picture directly on the surface of the building. So then it is environmental friendly. Okay, this is the first point. And the second advantage is that for horn antenna, if you want to achieve the beam sweeping, just rotate. But the angles is just let me give you okay. If you use the horn antenna, it means that if you choose this direction, you rotate this horn antenna. But the steering vector is fixed, has the structure. When we are writing the steering vector, it has a structure like a EJ, like something like the distance divided by the wavelength, right? It has a certain fixed structure. But for our MIS, as you know, that the phase shifts of these two layers can be arbitrarily designed, which means that the one thing is that this is for line of sight scenario. If it is not line of sight scenario, then if you use the horn antenna, it may not generate a beam towards the ultimate beam, that is best for the Russian channel user or the Russian channel users. But in our cases, because of the phases of the two layers can be arbitrarily designed. Actually, we can achieve arbitrary. What you need, an arbitrary channel. Okay, this is a arbitrary channel, and by achieving this arbitrary channel, we can use it in more complicated scenarios. Actually, as you can see here, we can although we use the line of sight for the illustration, but it could generate like if we have a lot of elements and this part, and And each of the, if this is the steering, for example, if this is a steering vector, and each of the layer, each of the elements, units, and their phase shift can be arbitrarily designed. That is beyond the structure of the traditional steering vector. Okay, it can be used like in other scenarios. So it has more, wider scenarios as compared to what you said. Use the rollable horn antenna. Okay.
Yeah. Thank you so much. Very clear. Maybe just a last second question. There is a hand raised by Mahmoud. Please feel free to unmute yourself and ask the question.
Yeah.
Yeah.
Thank you, Matthew, and thank you, Qingqing, for your insightful talk. Yeah, about the MIS. So my question is regarding like what I understood is for the MIS we can do the beam steering by the differential movement between two surfaces. Okay.
Yeah.
So my question is how easy it is to design and to control like the beam, like for example for a sensing task. So how can we, how easy it is to control the beam pattern, like the beam width and the resolution, like actually of the beam scanning? For example, because like what I understood is that we are constrained here for the MIS by discrete differential movements between the two misses. Yeah. So this discrete will form us like, or will constrain us with just like some discrete number of movements, But if I want to scan continuously a specific area or so, and I want to control the beam width and the peak to side loop ratio of the beam patterns, how easy it is with the design of that?
Actually, okay, very good question. Actually, I know where you pointed. That is, what I mean that if you move this surface and this is a discrete one, and if you want to, continuously scan, scan, I know how to do that. Actually. This is, the advantage, the ultimate goal of the MIS. That is, there are many structures. For example, we can also use multiple. Here we only demonstrated we use one, large IOS. Then you see that if we are moving this, 1 pixel, and you consider as a discrete. But if we have a multiple smaller, surface around the first signal, and it can achieve a more, high resolution of the sensing direction. This is the first point. And second point is that, and the phase shifts of this, of the first layer and second layer, based on our prior requirement, we can jointly design this. This doesn't mean that, for example, if we can jointly design the two, because these two kind of phase shifts can be jointly designed. This is what I mentioned as compared to horn antenna. Actually, to horn antenna, you only have one controllable, parameter. That is the direction. That's fine. But for the MIS, for each of the phase shifts, you can design in prior. And by using this kind of flexibility, we can, as long as you are giving like this, you are giving a requirement, you can just put your requirements toward the a continuous sensing. Actually, even you say continuous sensing, there is still in practice scenario there is still a resolution. As long as the resolution is given, we can design this kind of phase shift jointly with the movement with 1 pixel, 2 pixel. And then they are corresponding to what you want, the resolution you want. Okay.
Okay. So it's resolution specific. Yeah. Okay.
Yeah, it's resolution is specific. We are just trying to jointly design the phase shifts of these two layers and also the movement. Okay. This is not an independent design. Okay. It's a joint design. Okay. After the joint design, we can achieve your ultimate goal of the resolution in terms of sensing. Okay.
Yeah. Okay. Yeah. Thank you. Thanks so much. Thank you.
Okay. If you have the interest, we can also discuss later via email, and also you can read our paper online. Actually, we have a series of these works along this direction. Okay.
Yeah. Okay. Yeah. Thank you. Thanks so much. That will be interesting. Yeah. Thanks so much. Yeah.
Okay.
Yeah. Okay.
Okay. Thank you. Thank you so much. I guess this will conclude the talk. Thank you. Thank you again, Qingqing, for the very interesting and clear.
Okay. Thanks again, Mato. And also thanks for all your listening. Okay.
All right. Bye bye, everybody.